Okay, so today we're determining whether or not these demos that I'm going to perform are a chemical or a physical change. Okay, I'll do the first, so how many are there total? 6? 7? Is there 7? I'll do all but the last two. The last two are videos we're going to watch on YouTube, so anyone watching at home, I'll link those videos into the assignment as well. Or if you guys want to rewatch this video at home, you can watch these demos in the video and then watch those videos later. Okay? So for our first experiment, we have water, and we're going to mix in Kool-Aid. Okay? So when we're looking at a chemical reaction, we need to be considering the properties of our reactants. So water is a reactant. Okay? It's clear. It's not got any color. It's translucent or see-through. No smell. Okay? It's a liquid at room temperature. Kool-Aid, on the other hand, is a solid at room temperature, smells like berries, right? And has a blue color to it. Okay? If I mix these and stir them together a little bit, our final product is a blue liquid that kind of smells like berries and powder. And if we were to taste it, which we wouldn't drink out of a beaker, right? These aren't sanitary. It would have a very similar taste. So the question is this a chemical or a physical change? Okay, go ahead and write it down. What do you think? Chemical or physical change? No one got an idea? Let's go ahead and take a vote. Those of you who think it's a chemical change, go ahead and raise your hand. Good. Those of you who think it's a physical change. Okay, so the minority of people said that it was a chemical change. So let's see if they can convince us of their way of thinking that it's a chemical change. Jake, start us off. Why do you think this is a chemical change? Okay, we can't reverse it, you're saying? And we know that chemical changes are non-reversible. Well, or difficult to reverse. Okay? Either difficult or impossible to reverse. And so you're saying this would be impossible to reverse, therefore it must be a chemical change. Okay. Other thoughts? People who also did chemical thoughts. Yeah, go ahead. You think it's a new substance. How do you know it's a new substance? Has different properties. What are our different properties? Okay, so you're saying this blue color did not exist in our reactants. You're not sure? Let's ask the class. Did this blue color exist in our reactants? Yeah, where? In the powder. The powder had a blue color. So there was blue. Might not have been exactly the same shade, right? But there was blue. What about the smell? Did the smell exist in the reactants? It did. Where? Once again, in our powder mix, okay? So our properties are actually still the same. We're just thinking, we're focused more on the water than maybe we should be, okay? So are we certain? Let's hear physical changes. Let's hear some of those arguments. Abran. You think if I continually add water without more Kool-Aid, it would eventually get clear? Okay. It's a thought? Yes. Okay, so we don't have any new properties, just the properties that applied to the 2 now apply to the 1, right? So it's now a mixture. Braden? Okay, maybe we could use some sort of filter, like what you would use to clean water, right? If you use some sort of filter. In fact, I went camping once. It was for a youth conference, and all the leaders were getting their caffeine withdrawals, and so they had these caffeine squirt things they put in their water, but we had to use filters. And so I'm sitting there laughing because they were putting all this caffeine stuff in their water, but they couldn't figure out why they were still so tired. It's because that filter that they were drinking through was filtering out of the caffeine from their water. Anyway, it's kind of funny. Okay, so that's a great idea too. Okay, so if I'm understanding correctly, it sounds those of you who are talking about physical, how would you describe this? Is there a term you'd use for it? Because if I look at this, here's one of my concerns for those of you who are thinking physical. I mix this in, and this had a powder, and now when I look in here, there's no powder. Where did it go? It's gone. I can't see it anymore. Yeah. It dissolved. What does it mean to dissolve? Okay. Yeah. Okay. Okay. Yes. Okay. Okay. Interesting. Ben, you have any thoughts you wanted to add? These guys have covered it. Okay. So if I'm understanding right, you guys are saying that it's still there even though we can't see it. Kind of like if I was making cookie dough and I had my cup of sugar, I can see that sugar, but once I add that to the dough and I mix it all together, I can't see my sugar anymore, but I can taste it, so I know it's still there, right? So you guys are saying even though I can't see the powder, I can know that it's there because some of its properties still exist, like smell and color and so forth. So maybe this drawing right here kind of matches what you guys are saying, okay? So we have our beaker, and the black dots represent the water, the blue dots, the Kool-Aid powder. And they still both exist, they're just mixed together. Is that what we're saying? Okay, good. I'd agree. Okay, I'd agree. In fact, the biggest concern with this is students who are worried, well, can we reverse it? I did a little experiment today. Anyone ever boiled Kool-Aid? I'd hope not, because it ruins your pot. Okay, but I boiled some Kool-Aid today, and this is the Kool-Aid. That's the powder. Now, you need to ask yourself, why does it look like this and it's not a powder? Well, when I heat a liquid, what will it change to? A gas. The powder is a solid. When I heat a solid, it will melt into a liquid. So all that solid melted together, and there's sugar in this, and that sugar caramelized and crystallized and then burnt because I wasn't paying attention to it. And now it's all caked on the bottom of my beaker. Okay, but it's there. Okay? Oh, no, probably not. But I might have Ava try. Okay? Just kidding. I really don't think you'll get it out. But it was worth doing, right? It's worth showing that you can undo when something dissolves. Okay? So we've got a physical change, right? Everybody's on the same page with that. This is a physical change. Okay, for our next one, originally we mixed a liquid and a solid. Now we're going to mix a liquid and a liquid. And maybe that makes it different. So I've got food coloring here. I'm just going to put a drop of food coloring into my water. Now, if you want to do a fun experiment at home, mix food coloring in both hot and cold water. And don't stir it. Just see what happens, okay? But in this instance, I'm going to give it one little stir there. Okay? Now, was this a chemical or a physical change? Raise your hand if you think it was chemical. Think it's chemical? Raise your hand if you think it's physical. Okay? Ben, you raised your hand for chemical. Why do you think it's chemical?
There's new properties.
What are my new properties?
There's still no smell, neither. You know, I was going somewhere with that, and though now it is unreversible.
It's unreversible? Why?
Because you couldn't boil it.
You're right. They'd both evaporate. But could you use a filter like we were talking about earlier? Maybe. You potentially could, right? You could potentially use a filter and try and filter out that water. Okay? So are we saying that this was dissolved also? You guys are saying that a liquid can dissolve in a liquid? What do you think? Okay. So you're saying dissolving is probably not the right term this time. Instead, we just call it like mixing. And the red color is a very prominent color. And so as it mixes, just like in this diagram, we'd see the red. Okay, that's fair. Okay, so we all agree this is a physical change? Now here's my question. If we can mix a solid and a liquid and a liquid, can you mix a gas into a liquid? Can gases dissolve in liquids? Ben?
Yes, you can.
You can? Can you give me an example?
You told
Okay. Yeah?
Isn't there like little notebooks and hard problems?
So you guys are saying that fish breathe out the oxygen that's dissolved in the water. Now, a lot of people often think, okay, H2O, there's oxygen in water, in that molecule. The fish just break off, take that oxygen, and the hydrogen's left. Now, in this class, we've seen hydrogen, right? Hydrogen's very explosive, very high, or very light, right? It's a gas. So if that were happening, I want you to think about this for a minute. If fish were breaking apart water, leaving only the hydrogen left behind, that hydrogen's a lightweight gas. So wouldn't the lakes always be bubbling, right? You'd always have those bubbles coming up. And hydrogen's flammable. So wouldn't it be pretty easy to like light a bomb above a lake that has a bunch of fish in it, right? So once we logically break that down, we know that, okay, fish can't be breaking down those molecules, okay? Instead, we do have dissolved oxygen in the water, okay? Can anyone think of any other examples? Maybe of something that you consume that has dissolved gases in it? Yes? Soda, right? You have carbonation in your soda pop, right? That carbonation is carbon dioxide that's dissolved into it. What happens if you open a soda and you just leave it there for like 24 hours? Go ahead.
It's gone.
It's gone? The soda's gone? Someone drank it? The carbonation is gone, right? We say it goes flat is the term we use for it. Okay, so all those gases, they're high energy. And as they're high energy, they'll escape the liquid. That's just normal, right? The longer you have your soda open, the more flat it becomes, right? The more those gases escape. And so what happens then if you take your bottle of soda before you open it and you shake it up, and then you give it to your dad, right? Because you love him so much. And then he opens that soda, what happens? Right, we have this big geyser of soda. So what happened then that caused that to occur? Annalise, what do you think caused that to occur, that geyser of soda? Okay. What's them to mix? When you say it causes them to mix, what do you mean there? Okay, the carbon dioxide in the liquid. Okay. I think you're on the right track there. Any other thoughts? Now, the gas is naturally going to escape, right? And so do you think it would escape faster if it had more energy or less energy? More. If it had more energy, it would escape faster. Let me ask you this, too. Let's say right now we all had to rush out of this room, rush out of the classroom. Do you think that any desks would get moved? But we're not trying to take the desks out of the room. We're just trying to get you out of the room. But you think some desks would get moved? It's the same thing with the soda, right? That soda has a lot of carbonation in it, a lot of gases. You shake it, you're adding energy to those gases. The gases are now moving faster, and they're going to escape faster. And as they escape, they just bring some of the soda with them, right? Creating that geyser that sprays your dad in the face and grounds you for a week. Okay? Does that make sense? Okay. So that's dissolving things. Let's step away from dissolving things. Let's look at the instant snow. So that's the next one on your list is instant snow. Has anyone ever played with instant snow before? Ooh, a couple of you. Now, just so you guys know, in case you want to do this at home, I bought this at Hobby Lobby, okay? Because my wife is a Hobby Lobby enthusiast, and I ran away from her while she was looking at some ribbons and found this. It was $5 for this little vial, and I bought it with a 40% off coupon, and so it was only $3. So if you want to get your own, they're $3, not too bad to get there at Hobby Lobby. So I've got this powder. It's a very gritty, very small powder, and then I'm going to get 9 milliliters of water. Now I'm going to get really close to the camera here and try and hold it so all of you guys can see as well. But by holding this here for the camera, then anyone who's at home can see what's going on. Does that make sense? Okay, so I add in the water. And instant snow. Okay, and you can see there's enough here that it's even spilling over the edges a little bit. Okay, In fact, this snow reminds me a lot of Despicable Me because it's so fluffy I'm going to die. Okay? But I'm going to pass this around, let you guys feel it. Okay? You don't have to, obviously, but feel welcome to. Now, I've got to say, you guys aren't babies, right? Babies discover the world by putting things in their mouth that don't belong in their mouth. Don't put this in your mouth. I didn't think I'd need to say that, but I've been proven wrong once today already. Okay? Can we handle that? Don't eat it. I punch you in the face? I don't know. That might happen. Okay. Okay. So let's talk about it. Was it a chemical or a physical change? Let's take a vote. Who thinks it was a chemical change? Ooh, who thinks it was a physical change? Ah. Okay. So our physical changes are minority. Ava, why do you think it's a physical change? Is it a semi-solid? Have you seen it yet?
No.
Those of you that have seen it, would you call it a semi-solid, or is it still a powder? It's still pretty powdery. You probably didn't like pinch it, did you? You just kind of tapped the top.
Wait, what the heck? That's weird.
It's still a powder, isn't it? Can you guys tell? It's still a bit of a powder. Okay, so it was a powder before. It's still kind of a powder. What else, Ava?
Of it.
Okay, thank you. Okay, those of you that thought it was a chemical change, obviously you think a new substance has been created. What are our new properties then of this new substance? Tracy? It's fluffy? Is that what you said? Okay. So would an object becoming fluffy mean for sure that it's a chemical change? No? You're like, you wouldn't be asking otherwise. Because think about this. What about a balloon? Right? A balloon, before you inflate it, it's not fluffy, right? Then you blow up the balloon, and the balloon you could call fluffy, right? That squishy nature to it. So that's a maybe, right? Maybe. But it doesn't mean necessarily. That's not conclusive. Okay? Any other thoughts? Why it's either chemical or physical? Berto, what do you think? Don't sit on the fence. Make a decision. What makes you think one way or another? Maybe you think both, and you can tell us why you think both. Why do you say chemical? Okay, so once again, we're saying maybe it was gritty before, now it's more of a soft, fluffy nature. Okay, Aileen? Right, but we also say that a physical reaction, we also use that word for that too. So that's something to think about. Okay, yes? Don't think we can reverse it. You don't think, but do you know? You don't know. Okay, because a lot of us thought we couldn't reverse mixing Kool-Aid and water, and I reversed that today and ruined a beaker. Okay? So, those of you that are saying that it's chemical, you guys are focused on like one property that I just barely was saying could apply to both a chemical or physical, right? That it was gritty before, now it's more fluffy. But like I said, a balloon, as it inflates, becomes more fluffy, right? If you want to use that term. But are there other properties that have changed? Okay, so now you're even thinking like almost like a sponge, almost, right? Because a sponge at first, very, very hard, right? Then it soaks up water and it becomes very squishy and fluffy almost. Okay, so you're saying it's physical, it seems like a sponge even. Okay, so that would explain that change in property. Are there any other properties that changed that would denote that it's chemical? Yeah. It expanded. Does that mean that it was chemical, or could that also mean it was still physical? Blowing up a balloon expands. Getting a sponge wet, it expands, right? Okay, yeah? Okay, it stayed the same color. Didn't have a change in color. get it? Thank you. Okay. So let's take another vote. We've had some discussions. Who still thinks it's chemical? Who thinks it's physical? Wow, look at you guys. Hey, you feel pretty good to yourself. You think you convinced a lot of people there. Okay? This is a physical change. Okay? I love doing this because at first you're like, wow, that was so impressive. It's got to be chemical, right? But it's not. It's just like a sponge, like we were saying. It's just soaking up the water. Now, I'm sure you could dry this out, though I'll be honest, I've never tried, okay? Because I'd never bought it until this last weekend. I'd seen it before, but had never bought it. And we could run some experiments, heating it in a variety of different ways, trying to get it to dry out and see what happens. But anyways, that'd be, an experiment you could do on your own too. And I don't want to take away from you guys' experiences at home, okay? All right, pennies next, yeah? Okay, so for our penny, I want to remind you guys what a penny normally looks like. So a penny normally looks like this. Let me get close to the camera so they can see here. So a penny normally has this shiny color to it. My penny today looks like that, okay? So you can see the difference in the two, okay? Now what causes a penny to have this darker coloring to it? Yeah? Dirt? You think it's just dirt? So if I just washed it with soap and water, I could get that off? Okay, times it's been touched. Yeah? Okay. Okay. So you're saying it's kind of like rusting with iron, right? But what's a penny made out of? Copper. Okay. Right, you think it's oxidized similar to the Statue of Liberty. Good. Okay, so that's more or less what's happened. This, and obviously I can see a little bit of dirt on it, but that darker color is because the copper oxidizes. Okay, now is oxidizing, or rusting is what we'd call it with iron, is that a chemical or a physical change? It is a chemical change, right? It's forming a new substance. Just like the Statue of Liberty used to be that nice bronze color, now it's more of a green, and that was a chemical change. Okay, so I'm going to take my penny. Did I tell you what was in this solution yet? This is vinegar and salt. Okay, vinegar and salt. Another one you could do at home. Okay, I take my penny. Okay. Do you guys see the difference there? Okay. We've got a line like halfway through. There we go. Okay. So, did that undergo a chemical or a physical change? Clean the rest of it. Why do you say chemical? Change in color. So you're saying this bronze color didn't exist prior to the experiment, right? Yeah, that's what you're saying, yeah? Okay, so I'd agree, right? That shiny bronze-looking color did not exist prior to us dipping it in the vinegar and salt solution. Yes? That's right. When there's a chemical change, they're difficult to reverse. It is possible, but in order to reverse it, you need a new chemical change. Okay, very good. All right. So this was a chemical change, right? And we know that because one, it was caused by a chemical change, so we're reversing it with a chemical change. And two, it introduced a new color that was not in any of the reactants. Okay? All right, for this next one, it says burning magnesium, correct? So, this right here is magnesium. Okay? Now, I should wear my safety glasses here. It's a alkaline earth metal. So close. Okay? Now, so I don't burn myself, I'm going to hold it with these tongs. Okay? And then it burns really bright. So as it burns, I'm going to ask you guys not to look directly at it, But what's really cool, we'll close the door and we'll turn off the lights. Do you think you can handle that? Awesome. Okay, we'll close the door and turn off the lights and just watch the room. Okay, you'll see the room while we do this. Okay, and I don't know how well the video will work, but we'll see what happens. Okay. Okay, so go ahead and look around the room and you can see just how bright the room is without looking directly at this and hurting your eyes. Okay, you can turn the light back on.
How does it hurt your eyes?
It could just damage your retina because it'd be very bright for a short period of time. It's like staring at a flashlight, that sort of thing. It probably wouldn't do permanent damage. Not with that small of a piece, at least. Okay, but what's left was the smoke we saw in the air, and then this white residue. I'm going to hold it like this so they can see. Okay, yeah, here in my hand. So was this a chemical or a physical change? Jameson? Why do you say that? What were our new properties?
It's now white and powdery, and it's no longer a whole thing.
Perfect. It's white, powdery, no longer a whole thing. Other thoughts? Yeah? Yeah, burning is a chemical change. So anytime you see something that's burning, okay, so a chemical change will release energy. Okay? So when something's burning, it's releasing energy as heat and as light. Okay? So was there light released in this reaction? Yes. Just like glow sticks, right? Glow sticks are releasing light. So in this reaction, they were still releasing light, so we know that was part of the chemical change. Okay? For our last two, the balloons in liquid nitrogen and the elephant toothpaste, we're going to watch those as videos. So anyone who's watching this video, they can just check out those other videos. Okay? Any questions? Let's turn this off.